What's up guys, it's the Round Bottom Flask here, and welcome to our video lecture on stereochemistry. This is the part 1 of the said video lecture series. We'll be talking quite a lot here, as you see in the highlighted parts of the content. But don't worry guys, I won't take much long. I'll try to make it as concise as possible. So stereochemistry is basically the study of molecules in three-dimensional space, and that will include both how these three-dimensional arrangements of the molecules in space affect their physical, chemical, and biological properties, and as well as the manipulation of these spatial arrangements. So for example, we have this amino acid here, valine. Now if you notice in valine, in these two isomers of valine rather, there are what we call this. The bonds are the same. They're composed of the same atoms. The atoms are bonded all together in the same manner. However, there is one slight difference here. Is these lines that you see here? Now, this one represents the spatial arrangements of the bonds. So, a wedged line, like this one here, a wedged line represents that the bonds are coming out in front of the page, and the hashed bonds, like the ones on the right, are are the bonds that are coming out at the back of the page. Now we have introduced a new set of isomers here. Now these isomers of valine are what we call as stereoisomers, wherein they are they have the same they are formed using the same atoms, they have the same types of bonds, but their arrangement in three-dimensional space is different. Now let's have an example. Let's look at this picture here. Now in this picture of the chair of our right, when you place a mirror in front of it, it will produce a mirror image, right? But if you notice, this mirror image of the chair, you can actually impose it, or rather you can, what do you call this? Superimpose it. I think that's I can't think of another term. Superimpose it, or overlap it rather, while getting a perfect image, or while the image will look the same. Now, in your right hand, if you see in your right hand, if you try to look at your right hand through a mirror, the mirror image that you will see is actually your left hand. And if you try to superimpose the left hand to the right hand, not this manner, if you can see in the camera, not in this manner, but rather in this manner here, you will see that there will be a mismatch of the fingers, okay? Now, we say that our hands, may it be the right or the left, are what we call as a chiral object, because it produces a non-superimposable mirror of itself. That means, that mirror image, when you superimpose it to the original image, there will be a mismatch, so that means the overlap will not be perfect. Compared to an achiral object, such as the chair, if you superimpose its mirror image to the original image, the overlap would be perfect. Okay. Now, the same form of chirality is also observed with molecules, and that chirality is only observed when it has a tetrahedral carbon with 4 different substituents. So let's have an example here. Now, if you notice, a tetrahedral molecule with just 1 or 2 different substituents, if you try to overlap it with each other, there will be a perfect match. So the overlap will be perfect. Now, in this two substituent, carbon with 2 different substituents here, when you try to overlap this one, you just rotate it. You just rotate the molecule a few times, and the overlap will be perfect. Okay. Now, in a molecule with 3 different substituents, just like here in this one, no matter how many times you twist and turn the molecule, the overlap will not be perfect. There will always be a mismatch. Now, that tetrahedral carbon with 4 different substituents is what we call as a chirality center. Now, another way of what they call this, of viewing chiral molecules is that, or rather, another way of checking whether a molecule is chiral is if you check with using a plane of symmetry or a mirror plane. Now, a plane of symmetry, you imagine you place you cut the molecule into two by placing a plane between it, and if the left side is symmetrical with the right side, then it has a plane of symmetry. So for example, here in propanoic acid, if you place a plane of symmetry here going through this atom here, if you see, the left side is symmetrical to the right side. Now, in lactic acid, on the other hand, since we have one OH group on the right, but hydrogen substituent on the left, and this carbon here, when you place a plane of symmetry, the left side will not be the same, will not look the same as that on the right side. So this molecule, lactic acid, will be chiral. So let's have an example here wherein we check our chiral centers. So we have this molecule here, then we check how many chiral centers are present in this molecule. So we're given, so again, we just remember the criteria for a chiral center, so it should be a tetrahedral carbon with 4 different substituents. Now, remember, in the skeletal structure, if there is one bond missing in our carbon, in the carbon vertex here, like this one here, that means that bond is a CH bond. Okay, so this one here this is a different substituent, and it has a hydrogen atom here. Now since this belongs to a ring, what you can do to distinguish one substituent from the other is that you draw a line that bisects along to this reference carbon here. Now, if you see, this substituent is different than this part of this half of the molecule. Thus, this substituent is different, is unique rather from the substituent, therefore, this is a chiral center. Now, this one is also a chiral center with the same cases here, so let's reveal all of our chiral centers. This one, here, so we have a total of 10 chiral centers for this molecule. Now, there are several types of stereoisomers. And I will only discuss about enantiomers and diastereomers. Now, geometric isomers, we have already discussed that. One example of a geometric isomer is your cis-trans isomer. I will only discuss enantiomers and diastereomers. Now, enantiomers are isomers who are non-superimposable mirror images of themselves. That's actually just a definition. These are isomers that are non-superimposable mirror images of themselves. Now, a molecule that only has one chirality center only has 2 stereoisomers, which are enantiomers. So, in paper, one way of representing the configuration of stereoisomers is through the RS configuration. So we have 2-bromopentane here. So how do we tell one stereoisomer of 2-bromopentane from other stereoisomer? It's not even written, even just using its IUPAC name, it doesn't give you an indication on what stereoisomer is represented. It's at least more general, But with the RS configuration, we can identify one stereoisomer from the other. Now, how do we assign? Now, RS configuration are actually assigned to your chirality centers. So, how do we assign this RS configuration? Now, the first thing that we're going to do is we have to use the Ingold-Prelog rules and assigning priorities to the substituents on the tetrahedral carbon. I will show you later on how do we use the Ingold-Prelog rules for what they call this, for assigning priorities to our substituents. Now, the lowest priority, which is number 4, since we only have 4 different substituents in a tetrahedral carbon, is positioned at the back of your chirality center. Then after that, you draw an arrow from 1 to 3 as if you're driving a steering wheel. And if the arrow moves to the right or moves in a clockwise direction, then the configuration is R, which is short for rectus, which is a Latin word for right, and S will be, and counterclockwise or a direction going to the left of the move, with the movement of arrows, the configuration will be S. So how do we use the Ingold-Prelog rules? Now, the anchoring principle is simple, is that you rank your substituents according to atomic mass. Now, the higher the atomic mass of the substituent, the higher will be the priority. That's just simple. Now, it becomes more complex when your substituent is composed with more than one atom. Now, for example, you have a substituent wherein, like this one here, like the ones shown in the examples here, which is composed of more than one atom. So what you do first is you look at the atom directly attached to the chiral carbon. Now, if the atom directly attached to the chiral carbons are the same or has the same atomic mass, you move to the next you move to the next atom directly attached to that atom directly attached to the carbon atom, or rather, to make it simpler, you move to the next atom of attachment. Then you repeat this until a first difference is found. So let's have this example here, a CH3 group versus an ethyl group. Now, a methyl group, if this is their point of attachment, now a methyl group, the first atom of attachment will be carbon. Same goes with an ethyl group. Now, they do not have a difference. Now, since they are both carbon atoms, you move to the next carbon, to the next atom. Now, the next point of attachment for your carbon will be hydrogen. The next point of attachment will be hydrogen. Even if you go above, it's hydrogen and hydrogen here. Now, for the ethyl group, the next point of attachments will be 2 hydrogen atoms and 1 carbon atom. Now, you have already found a difference here. That means we can now set a priority. Since carbon is higher in atomic mass than hydrogen, therefore, this one will be given a higher priority, as shown here. Okay? Now, let's, this two here, these ones here, they're pretty simplistic. So, let's have, this one here is pretty simplistic. So, let's have this one here. So, this one here, they have 2 points of attachment. So, they have a difference here. They don't have a difference in the first atom, which is carbon, and this atom, the atom directly attached to the first atom, which is also carbon. So you look for the other atoms directly attached to the first atom. So here, these are the same. These are the same hydrogen atoms, but however, there is a difference here, where in this case, this is a carbon atom, Well, in this case, this is a hydrogen atom. Now, since this carbon is a higher priority than hydrogen as based on rule number 1, therefore, this substituent will be given a higher priority. Now, the last one here will be kind of tricky because it has a higher priority when you base it here, but it has a lower priority when we base it here in this atoms here. Now, the point here is that this is already a difference here, and this is a difference here. Okay? This is already a difference. So therefore, when we compare these two, this one will be given a higher priority since chlorine is heavier than nitrogen. Now, even if we compare chlorine to the other 3 atoms shown here, to the other 2 atoms in this substituent here, chlorine will still be given a higher priority since it has a higher atomic number, or rather a higher atomic mass. Now, in multiple bonded atoms, in multiple bonded atoms, the difference, rather, what do you call this? The multiple bonded atoms, you treat them as if they were singly bonded atoms. So let's have this one here. So this carbon, this carbonyl group, or rather this carbon is bonded to, is doubly bonded to oxygen and singly bonded to hydrogen. So we can actually say, so this is actually equivalent to this carbon atom singly bonded to 2 other oxygen atoms. Now this oxygen atom is doubly bonded to a carbon atom, and we can say that this oxygen atom is bonded forms a single bond with 2 other carbon atoms. Now, remember that this oxygen here is just what they call this? It's just a hyper-realistic representation. It's a hyper-realistic representation of this single oxygen atom. So that means these actually represent a single entity. Okay, so you can imagine it's like it's like an ice cream. I don't know. It's like in your ice cream you have 2 flavors in one, but actually it's just the same container. It's just that you have still the same ice. It's still ice cream, but you just separated it into 2 distinct flavors. But it's still within the same container. It's actually something like this. I hope you get the analogy, guys. So let's practice our assignment for the Cran-Ingold-Pellet rules. So let's have this one here. Now, so what I do, since this is multiple bonds, what I do, this one first, for letter A, I try to break this down to multiple atoms, as we have seen, to single bonds, as we've seen in rule number 3. So this is equivalent to a carbon atom singly bonded to 2 other carbon atoms and 1 hydrogen atom. And this carbon atom is singly bonded to 2 other carbon atoms. So it's singly bonded with 1. This is already 1 single carbon-carbon single bond. Then we draw another carbon-carbon single bond. And that is equals to 2 other hydrogen atoms. Now this one here, we break this down. So this is C, H, C, C, H, 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 oops, it's a bit messy. So we break this down, it would look like this. So what I just did here is I broke it down to their individual Lewis structures. So this one, I'll write it down here because it gets messy. See, oops. Yep, I'll try to draw it here. It's crowded over here, guys. So I'll just draw it here na lang. I hope you can still see, despite my presentation. Oops, yeah, it's not that visible. I'll move myself out of the way. Whoops. Then we have this one here, which is simply a simple CH2 CH3. Now, if you look at the first the first atom from the point of attachment, so this will be carbon, 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 carbon. So they all have the same atom. So we need to move on to the atoms directly attached to it, to the first atom. So we have 2 H hydrogens here and 1 carbon here. We have 2 carbons here and 1 hydrogen here. We have 2 carbons and 1 hydrogen, and we have 3 carbons. Okay, now obviously, since this is 3 carbon atoms, this is only 2, 2, and 1. So obviously, since it only has 1 carbon atom and 2 hydrogen atoms, and hydrogen atoms are lower in priority compared to carbon in terms of according to the Cann-Ingold-Prelog rule. So this will be our priority number 4. And since we all have 3 carbon atoms attached to it, while in this case it only has 2 carbon atoms, then the next level of priority, then this will be our priority number 1. Okay, so we're done here. So we can delete this one. So we just need to figure out which is number 2 and priority number 2 and priority number 3. Oops, sorry. This is priority number 1. So we just need to figure out which is priority number 2 and priority number 3. So since they both have 2 hydrogen atoms and 2 carbon atoms and 2 hydrogen atoms, 1 hydrogen atom rather, attached to the first atom from the point of attachment, we move on to the atoms directly attached to the second atom. So we have carbon, hydrogen, and hydrogen here, while this is hydrogen, hydrogen, and hydrogen here. So since we already have a difference here between this one here, and carbon is a higher priority than hydrogen, so therefore this will be our number 2 and this will be our number 3. Okay? So we have this one. So we break it down here. So that is C, 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 and C, 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 H. It would look like that. Since a triple bond, it means that the carbon is attached singly bonded to 3 other carbon atoms. Okay? So we have already seen this one. We have already seen this one. And this one here, we have not seen this, so we will try to break it down. So this is an aromatic ring, and we have carbons connected with each other in a ring. So that is 1, 2, 3, 4, 5, 6. Now, since there are double bonds here, so it is singly bonded to 1 carbon atom and is doubly bonded to another carbon atom. That means it is connected to it is equivalent to a carbon atom singly bonded to 3 other carbon atoms. So if this is our point of attachment, so we have another carbon atom here. So we have 1, 2, we already lack a carbon atom here. Since we still have we have a missing bond here, that means the other bond will be a CH bond. So we draw our CH bonds here. This will also happen here. So the cycle repeats, and so on and so forth to all of the atoms in the ring. Now, this one we have already seen here. Obviously, this will be our... So obviously, since we have already seen that this is higher in priority than this one, this is lower in priority than this one. And obviously, if you see here, if you look at this structure here, this is obviously higher in priority than all of them, because in the first carbon atom, but in the first point of atom of attachment, it is already attached to 3 other carbon atoms. Now, in this case here, although it is attached to 3 other carbon atoms, however, then their next point of attachment, is that the carbon is attached to 3 other hydrogen atoms. Well, the next point of attachment here is that the carbon is attached to 2 other carbon atoms and 1 hydrogen atom. So obviously this will be a higher in priority than this one. So this will be our number 1. Okay? Sorry guys, I'm a little bit under the weather today. So now this carbon here, now obviously since this is lower in priority than this one, so and if you see here, this carbon is attached, this compound, the first carbon is attached to 1, 2, 3 carbon atoms, while we have seen this one that this is attached only to 2 other carbon atoms and 1 hydrogen atom. So obviously this is higher in priority than this one. So this will be our number 4. Now the tiebreaker will be between this substituent and this substituent here. Now this substituent is, I'll draw it again. Is attached to 1, 2, 3 other hydrogen atoms, while the next carbon is attached to 2 other carbon atoms and 1 hydrogen atom. Now there already a difference both here. Okay? So, since carbon is heavier than hydrogen, therefore, this will have a higher priority than this substituent. Therefore, this will be our number 2, and this will be our number 3. Okay, I hope you understand, guys. So let's from the assigning the priority. So let's try actually assigning RS configuration. So let's try for this example here for letter A. Now, convenient for us, H is already at the back. The lowest priority, which is hydrogen, obviously, is already at the back. Then we need to know which is the priorities 1, 2, and 3. Obviously, since chlorine is heavier than carbon in terms of atomic mass, so therefore the chloro substituent will be given a priority number, the first priority, or priority number 1, and between these two substituents, obviously this will be given a priority number 2, and this will be priority number 3. Because this is a carbon, and this carbon is attached to 3 other carbon atoms, while this carbon is attached to 3 other hydrogen atoms, and the carbon is heavier than hydrogen, so therefore this will be given a higher priority. So this will be the order of priority, the assignment of the priorities of the substituents in the tetrahedral carbon according to the Can in Gold-Prelog rule. So since number 4 is already at the back, so we can draw the arrows here, and based on the direction that is a clockwise direction, so the compound will be R. So this is a clockwise direction, therefore the compound will be the configuration of the compound will be R. So let's proceed to the next. Now, one trick that I've learned is that we don't need to actually imagining the molecule flip in our heads so that the lowest priority substituent will be behind. Okay? So we don't need to imagine this in our heads. So the one trick that I have learned from my colleague, shout out to Ma'am Josie Rojo of the UP Visayas, if you're watching this, I hope. So one way is what I did is this: I assign already the configuration even before the fourth lowest priority substituent was placed behind the back. Now let's try to assign priorities to this one. So H. So obviously H is the lightest among the atoms directly attached to the tetrahedral carbon here. So this will be number 4. And we know that oxygen is what do you call this? Oxygen is heavier than carbon in terms of atomic mass. So this will be number 1. So both of these atoms here will compete for the priority numbers 2 and 3. So in this case, since they are both attached to carbon, we need to look next on the next point of attachment. So we expand this substituent here to their respective Lewis structure. So this substituent here is actually a C double bond OOH group, so it would look like this. And this will be C . Now since there is a double bond here, we deconstruct this again. So this one here, the double bonds represent that the carbon is it is equivalent that the carbon is singly bonded to 2 other oxygen atoms. So it would look like this. And the oxygen atom is singly bonded to 2 other carbon atoms. So it would look like this, and this one, this is already its very, very reduced form. So if you see that this carbon is attached to 3 other oxygen atoms. Now you will not find a difference here in this oxygen atom, but in these 2 atoms here, there is already a difference. And since this one oxygen is heavier than hydrogen, therefore this substituent will be given a higher priority than this substituent. Therefore, this will be our numbers 2, and this will be our substituent number 3. Now, if we trace the arrow from 1 to 3, so it would look like this. So the movement of the arrow will be R. Now, if you flip it 180 degrees, it would look like this, and the movement from R and the movement from clockwise will be counterclockwise, and that is S. Okay? So therefore, the configuration of our molecule on letter B will be S. Okay, now what is the purpose here? What is the gist here? So what you do actually is, if the hydrogen molecule is not at, if the lowest priority substituent rather is not at the back, is if it maybe it be at the front or at the sides, you assign what they call this. You try to assign configuration, the RS configuration, even before flipping the molecule. Now, when you assign the RS configuration and when you flip the molecule such that the the fourth priority substituent is at the back, the configuration will also flip. So if in this case, if the fourth priority substituent is at the front, its configuration will be R. When you flip it 180 degrees such that the fourth priority substituent is at the back, the configuration will change from R to S. And if this is S, and if you flip it 180 degrees, it will change to R, and vice versa. So that's the trick. That's the trick here, guys. So you don't need to imagine. You don't need to imagine the molecule going flipping at the top of your head. You just try to trace the arrows. Then, if the lowest priority substituent is at the front, and when you flip it at the back, the actual configuration will be the reverse of the initial configuration. So, for example, again here, if this is R, wherein the lowest priority substituent is at the front, the actual configuration will be the one wherein this one is at the back, as shown here, wherein we flip 180 degrees, and automatically from R, it will change to S, since we only have two possible configurations here, R or S, right? So, that's one thing you have to remember, guys. So that you don't need to flip the molecule first before figuring out the RS configuration. So what I do is figure the RS configuration beforehand, then flip the molecule. The actual RS configuration is the opposite of the first configuration that you've thought of before flipping the molecule. Next is lastly, we have this one here that has more than one chirality center. So what I usually do here is I try to I analyze the chirality centers one by one. So based on the naming of our compounds, obviously our carbon number 1 will be the one that is directly attached to the acyl group. So will be our carbon 1, this will be 2 and 3. Okay? So let's try the easy one first, the chirality center at carbon 3. So since the carbon 3 is part of the ring, so what I do is I draw a line that bisects along carbon 3. Then I treat this side of the ring as a different substituent than this one. Now obviously, hydrogen is the lightest element, the lightest atom here, so that will be your number 4. And comparing the methyl group with these two other substituents here, obviously this will have a lower priority, so that will be our number 3. Now, the first point of attachment will be carbon here. They are both CH2 groups, so they have a tie with the 2 hydrogen atoms. Then we jump next to the next point of attachment, which is also a carbon atom. Now this one here has only one other carbon atom directly attached to it, while this one here has 2 other carbon atoms attached to it. obviously this side will be given a higher priority than this one. So therefore, sorry, excuse me guys. Therefore, this one here will be our carbon 1, or rather our priority number 1, and this one will be our priority number 2. And based on the direction, rather, this is 1, 2, 3. So that is a counterclockwise direction. That will be the configuration will be S, and since it is at carbon 3, that will be 3s. Next is we have we go to the other carbon atom here. So we also use the same trick as the one here. We also use the same trick here. So first we figure out the configuration even before flipping the molecule, such that the lowest priority substituent is at the back. So just like what we did in carbon 3, we bisect along carbon 1. Then we assign our substituents. So this is obviously carbon number 4, and this is obviously number 3, and this is carbon 1, and this is rather priority number 1, and this is priority number 2. And this molecule, if we trace it from going here, so that is actually R. So this is a clockwise direction. So this is actually a clockwise direction. So the configuration is R. Now, since it is R and the hydrogen and the forced priority substituent is at the front, not at the back, we rotate this along the carbon 1 axis, and we can see that in this case here, and this one here becomes S. From R it becomes to S, and since the forced priority substituent is at the back, this will be the actual configuration at carbon 1. So the configuration will be 1s 3s. Okay. So this is the end of my video presentation. I hope you guys have learned a lot from it, and if you do, don't forget, and if you find this video interesting, don't forget to subscribe to my YouTube channel for more videos. Once again, this is the Round Bottom Flask. See you guys